So yeah, in the previous video we talked about the confusion matrix, which we can use to compute the number of true positives, false positives, true negatives, and false negatives, and then also the true positive rate, false negative rate, and so forth. So now we are going to extend the concept to three additional metrics called precision, recall, and F1 score. So let's start with the precision. So how is the precision computed? It's computed by the number of true positives divided by the true positives plus false positives. So if you think about true positives and false positives, so these are the ones that are predicted as positive. So in that sense, predicted, if we take a look at the spam example again, these are predicted as spam email. So these are spam that is predicted as spam. And here are all the ones that were predicted as spam, which also includes the false positives, so non-spam email predicted as spam. So what does the precision gives us then in terms of the information? So what the precision gives us is the number of actually correct predictions, positive correct predictions out of all the positive predictions. So how precise is our classifier? How many of the actually predicted spam emails are actually spam? So that's the precision. Another metric is the recall, which is actually the same as the true positive rate that we talked about in the previous video. So that's the number of true positives divided by the positives. And so this one gives us how many of the positives do we actually recall. So the true positives are the ones that we correctly predict as positives. So how many out of the positives do we actually identify as positive? It's like, how are we doing on recall? How many do we actually identify as positives given all the positives? And a weighted version of the two, of precision and recall, is the so-called F1 score. So the F1 score, you can think of it as a combined version of precision and recall, which is using both and then multiplying it by 2. So the range of all these metrics is between 0 and 1. So I'm writing here, I see in my notes that terms that are more so these are terms that are more popular in information technology. By that I mean there are other terms called sensitivity and specificity. Sensitivity and specificity are terms that are, I would say, more popular in computational biology, for example, whereas precision and recall are terms that are more common in information technology or computer science and machine learning. So if you would write a paper, for example, for a computational biology journal using machine learning, then maybe using precision and recall is not the best idea, because most people in computational biology use sensitivity and specificity to analyze their systems. So like I said, recall is actually just another term for the true positive rate. Here's a helpful visualization of the precision and recall that I took from Wikipedia. I kind of like this visualization because it's just easy to see what's going on. So you can think of everything here on the left box as the positives, in the case of spam classification, the spam email, and these as the negative class. And then the precision is computed as the fraction of the true positives, so that's the true positives over all the predicted ones. So these are all the ones that are predicted as positive. So that's the fraction of the actual positives, the true positives predicted as positives, over all the ones predicted as positive. Whereas the recall gives us the number of true positives over all the positives, for instance. So here's just a helpful visualization of this metric of the precision and the recall. Now, like I said, there are two other metrics that are commonly used, for example, in computational biology. It may also be common in other fields. I didn't work in many other fields except machine learning and computational biology. I know for a fact in computational biology, when you talk to biologists, Most of them are familiar with sensitivity and specificity. However, in computer science, if you mention sensitivity and specificity to someone, most people don't know what that is. Most people are familiar, though, with precision and recall. In any case, sensitivity is just the same as recall. It's just another word for recall. Specificity is a little bit different. It's the number of true negatives over the number of negatives. So it's kind of the opposite of sensitivity. I think it's kind of intuitive to remember it like this, because here you have the true positives over the positives, and for specificity you do the same thing except for the negatives, the true negatives over the actual negatives. Alright, so it's sometimes people also say it measures the recovery rate of the negatives, whereas the sensitivity measures the recovery rate of the positives. Okay, so lastly, there's one more thing, that's Matthew's correlation coefficient. And this is also something that is commonly used in the context of biology, originally for assessing the performance of protein secondary structure predictions. So what is a protein secondary structure prediction? So if you think about amino acid sequence, so where you have an amino acid sequence like as follows. It's not a DNA sequence, it's an amino acid sequence. And then from the sequence, you can predict whether a subsequence is in a 3D structure, for example, in an alpha helix or in a beta sheet and so forth. So you're predicting alpha helices, which are three-dimensional structures, based on the sequences. So in that way, there are algorithms to predict that. And Matthew's correlation coefficient was back then formulated to assess the performance of these prediction algorithms. So you can think of it as a version of a linear correlation coefficient, but instead of like a Pearson's R for linear regression, you would have that for a binary classification setting. So it's like a correlation coefficient for classification settings. And sometimes also it's often regarded as useful in imbalanced class problems, where you have a problem where one class has more examples than the other. So in some cases I see that also recommended for imbalanced class problems. So the previous metrics that we talked about, specificity, sensitivity, recall, precision, F1 score and so forth, they were ranging between the values 0 and 1, where 1 was best. So Matthew's correlation coefficient now ranges from -1 to 1, similar to Pearson's R correlation coefficient. So Pearson's R also ranges between -1 and 1, where if you recall Pearson's R, if you have -1, you have a negative correlation. For a 0, there is no correlation. And for a 1, there is a perfect correlation. And analogously, for Matthew's correlation coefficient, you have a perfect correlation if you have a 1. So that means that you have a perfect match between the actual ground truth label, so the true label, and the predicted label. And if you have them completely flipped, if you predict every positive as negative and every negative class as positive, then the correlation coefficient would be -1. And if the prediction is completely random, then you have a value of 0. I think it's kind of intuitive and useful also in practice, just to see how your classifier performs. So for example, if you see that your classifier has a -1 in terms of the Matthew's correlation coefficient, it might be just useful to flip the predictions, and then you have a perfect classifier. Okay, so that's Matthew's correlation coefficient. Here are lastly some code examples for the different metrics that we talked about. So here's just again what we had before, our k-nearest neighbor classifier together with a standard scaler on the Wisconsin breast cancer dataset. And this is the confusion matrix that we had. And then we don't actually need to use the confusion matrix, it's just for reference. We can import the scores, like the precision score, recall score, F1 score, and Matthew's correlation coefficient from scikit-learn. And just apply them to the test labels versus the predicted labels and get the different metrics. That's how you can use it. So you could technically also just compute that from the confusion matrix, but that's not necessary. So we can also use these metrics in grid search. So instead of providing, for example, these function as input, you can also use a string, for example, F1 for F1 score, or the string precision for precision, and then do grid search and hyperparameter tuning with these metrics instead of using the classification accuracy. Note that for multi-class problems it's a little bit trickier because all these metrics we discussed so far are binary metrics, so they only work if you have two classes like 0 and 1. So if you want to use, for example, precision, recall, or the F1 score for multi-class, then you have to do a little workaround. So you would use the make scorer function and then make a scorer using, for example, the F1 score and set the averaging to micro or macro. We will talk more about micro and macro in the last video in this lecture. But yeah, if you want to do that, then here, I mean, if you are basically trying to do a multi-class problem and it doesn't work using F1 score, then you know it's because you probably didn't do the average, and what that means will be discussed in the last video. And yeah, we can then provide the scorer also to the grid search, and this is how we can use different metrics instead of just classification accuracy to do the grid search. Okay, this was probably more of the boring videos because we just went over some additional metrics. In the next video I will talk about balanced accuracy, which is another of these metrics. It's a modification of the accuracy, which is actually useful if you have an imbalanced class problem, and this is also then can be used for multi-class actually. So this will be also interesting, and then we will talk about receiver operating characteristic curves and then extend the binary metrics to multi-class settings. Okay, so I will see you in the next video.